A few years ago, I taught myself how to do some basic card magic. I love those moments of wonder when you successfully pull off an illusion. As front-end engineers, we are masters of creating illusions. We take information that has no inherent physical form and somehow do some trickery to allow that information to be consumed by people and for them to interact with it as well. One illusion that I created is react-beautiful-dnd, or RBD for short. RBD is a library for React that provides beautiful and accessible drag and drop for lists. RBD attempts to provide an experience that feels physical and relatable for human beings. RBD is ultimately an illusion that is powered by misdirection and sleight of hand. And today I'm going to reveal to you how the magic of RBD works so that you can use its techniques in creating your own illusions, or that you would be inspired to try something unusual. So cool, first up we have this application, and we've got a user and they're going to move their cursor over the item and they're just going to click and drag it. Cool, simple enough, right? Now to get to this point, RBD has probably done about 10 different tricks. I'm not sure if you saw any of them, and that's good. Okay, so let's have a look at what they are. So first up we have an item here, and the user's going to move their cursor or pointer over that item, and we're going to need to want to know about some user input. So we're going to add an on mouse down event listener just with React, and after that we're going to bind some other events to the window. Things like mouse move and key down that we're going to need for the rest of the drag. Now we're binding them to the window because sometimes the user's input can slip off the edge of the element that we're dragging. And if that happens, we still want to be able to capture all that input, so that's why we're going to add it to the window there. But this approach has problems. So yes, there we go. Sometimes the dragging item can be removed during a drag. So this can happen when the item you're dragging, you move it into a React portal, which is just a fancy word for another element on the page. You can move it over there. Or if you're using virtual lists, sometimes the element you're lists in the virtual list can get junked. So we can't necessarily tie these events to that element. I didn't mention here, but there's a little bit of state, and that's the fact that these events have been bound. And these events will need to be unbound at some point, and so when the element's being unmounted, it's going to need to unbind these events, which should mess up our drag and drop. So instead, we use this concept called a sensor. So we add an event listener to the window directly, say a mouse down listener, and we inspect the events that are coming through, and we check to see if they're coming from a draggable item. And we know they're coming from a draggable item if it has matches a data attribute on that element, which we put on there. And if it does, we can also grab the ID of that thing, so we know the thing that they were trying to grab. So that's cool. So then after that, we can again bind these event listeners to the window, but if that original element gets junked, it doesn't matter, because that state of knowing whether or not the event needs to be bound or unbound isn't tied to the element at all. In a more general sense, in RBD, a sensor is responsible for giving instructions to the application that RBD understands. So things like move up, move down, lift, drop, that sort of thing. And usually they're mapping user input, like mouse moves, to those instructions. RBD ships with 3 sensors out of the box. So we have mouse, touch, and keyboard. But we also have an API where you can roll your own. So you could drive a drag and drop using really any user interaction you can think of, whether that be like joystick or movement. It's kind of up to you. But as well, they can also be programmatic. So it doesn't actually have to be user input. It could just be a run sheet. That's fine, and that will work all good. Now, with all these sensors floating around, how do we ensure that they don't fight against each other so that we don't accidentally have 2 of them trying to drag at the same time? And we introduce this concept of a lock. And this is the same concept you'll find in databases, where if you want to do an operation across multiple tables and you want to make sure that people aren't going to mess up your stuff, you can kind of like lock parts of things so you get exclusive access and no one else can get in. It's the same idea here with the sensors. So a sensor will request a lock, and if it gets it, it can then have exclusive control to drive that interaction. So if another sensor comes along and says, hey, I want to start doing some stuff, it'll just say, nah, you can't get the lock, you can't do anything. All good. These locks can be released when the user does a drop or cancels. And we can also purge these locks. We can force the sensor to release it in an error scenario, and it's up to the sensor to clean itself up. If the sensor tries to do stuff with that outdated lock, it won't do anything. It'll just log stuff to the console saying, hey, your lock's outdated. Cool. Taking a step back from the details of sensors, we have this concept of a sensor, and it's telling the app, RBD, hey, we want to start a drag. So what do we do from there? Well, the next thing RBD does is that it collects a snapshot of every single DOM element that it cares about all at once. So how does it do it? So when the components mount, they register themselves with a registry that is populated down the context of the React tree. So they say, hey, here's some details about myself, and here's a callback that you can get my underlying DOM node at a later point. And then another thing will come along at that later point and call all those callbacks to get all the DOM dimensions so that we can build up a map of all of the positioning and spacing information that we need for this operation. And this kind of raises a theme that I'll be revisiting as well, is that drag and drop is a very performance-sensitive problem space. The React reconciliation process is amazing. It's kind of like the magic source of React, where you update some state and you re-render and your UI reflects that state. But it can be expensive at scale. So where at all possible, we try and sidestep React to avoid needing to go through that pipeline to make things as fast as possible. This theme of work avoidance will come up again later as well. So great, we have this list and we want to start moving it around. What do we do? Well, first thing we're going to do is we're going to apply position fixed on that item. The reason we're doing that is because sometimes you can have all these parent styles that can mess up your layering. And what position fixed will do is remove that element from the document flow. So you're less susceptible to some weird stuff going on in your parent styles. We can also move it to a React portal, another DOM element, usually just a child of the body element, which doesn't really have any parents or many parents, so that we're not going to get hit by some potential CSS layering issues. Cool. But that has some unintended consequences. So the first problem we have is that the element shape has changed. When we removed it from the document flow, its size can change, because often an element size is controlled by the constraints of its parents. Also, the lists in the item, the items in the list have bunched up. That space that dragging item was taking up has now collapsed. So all the things that were being pushed down by that space have now shifted up on the page. That shifting up has also caused the list to shrink, because there's just less stuff in there now, right? So all this weirdness has happened. So how do we get around that? Well, we use that snapshot that we previously collected, and we use that to lock the dimensions of the dragging item. So we know what its width and height were before it started dragging, and so we just pump that back onto the item using an inline style. So we kind of lock it visually so it looks the same even though it's been removed from the document flow. Now the space it took up has collapsed. So what we do is we instantly shift everything that would have been shifted up on the page, we shift it down all at once. And we shift it down by the amount of space that dragging item would have taken up. So that space has technically collapsed, but we've just counteracted that by shifting everything down. So visually it looks like nothing has changed. And thirdly, we insert an element into the end of the list, which takes up the same space as that dragging item to stop the list from collapsing. In film editing, this is known as an invisible cut. So a lot has changed between these two frames, but it's just not perceivable to the user. To them, nothing has changed, but really we know a lot has changed. Now you might be thinking, hey, that sounds expensive. Pushing all these things down all at once is going to be a lot of work for React, and it is. So what we do in RBD is we employ windowing. The big idea of windowing is avoiding off-screen work. There's just no point doing stuff that the user can't see. All right? So we don't bother to shift down these items that the user won't be able to see anyway. So you can see there's like a little holiday emoji. Those ones will actually shift up in response to that space being collapsed. But you just won't see it, right? If you could see beneath the bottom of your viewport, you would actually see some of these items shuffling up a bit, but you can't see beneath the bottom of your viewport, so you won't see that. So there is a little bit of nuance here in that you'll see that this item right at the bottom is technically not in the viewport, but it's still being shifted down. And that's because when we're thinking about windowing and this space collapsing, we're not just looking at what's visible now, we need to consider what would be visible if this collapse happened. Like if this collapse was to occur, this one would shuffle up and become visible. So we need to push it down, even though it's technically not visible at the time that the drag happened. So there's a bit of nuance here to get that working correctly. Cool. Sometimes we want to apply styles on bulk to a lot of components at different points in the drag and drop lifecycle. Usually these are non-visible styles to do things like opt out of some WebKit mobile behavior. So how we do this is we create a style element in the head and we target each of these elements using a data selector. Like usually when you're writing CSS, you can target elements you're usually using like class names or IDs. You can target them using a whole lot of other things, including attributes. So we use this data attribute to target them. We can apply styles to all of them using that method. As a side note, it's kind of nice as a library author to provide a data attribute for people to apply. If you're giving them a class name, they may need to merge it with their own class name. They may override their own class. Like you might get some clashing going on. We can just sidestep that whole issue by, in this case, passing a data attribute, which is pretty nice. So as I mentioned, we update these non-visible styles at different points. Usually when you're updating styles in React, you are doing a re-render of a component to either change a class name or an inline style, okay? But that would be expensive at scale to do for everything. And this would be especially bad during a drag and drop where we want things to feel really buttery. We don't want any moments of jank. So what we do instead is we replace the entire content of that div all at once. So that way we don't need to pass down any new IDs, any new classes, any new attributes. We just swap the whole thing out. So we can change the rules that are being applied to these elements at different times without needing to ask React to do anything. And that's pretty cool. And it turns out this is wildly fast, which is great as well. Cool, so here we are. We've got this app and we're ready to go. What do we need to do now to get this thing to move? Thankfully, it's just as simple as applying a transform on that item. You know, we're going to listen to this input from the sensor and we're going to move this thing around using a transform. All good. But we're going to want to move these other items out of the way to make space for this dragging item. So how do we do that? And this is where our collision engine comes in. So the collision engine is a small physics simulator which takes the sensor's instructions, the snapshot, and calculates what displacement the dragging item would cause. The displaced items move out of the way by the size of the dragging item, and they move out of the way using a CSS transition. As much as possible, we try and use CSS animations so that we can offload as much work as we can to the GPU. Anything we can offload off the main thread, like just absolutely go for it. It's going to make your performance much better. So we just go, yep, just GPU, you take care of that so we can make the main CPU less busy. Cool. Now these animations that we use to move out of the way were hand-tailored by a prototyper at Atlassian called Jake Miller, and he's sort of gone through and figured out a curve that is intended to communicate something getting out of the way. There's been a lot of thought put into that animation curve as well. So I mentioned before that we insert space into the list or the dragging item to stop it from collapsing. And in this example here, I've highlighted that in green. This is the actual placeholder that I've just put some styles on so you can see what's going on. Now, when we move into other lists, we also need to make space in those lists for the dragging item. And that's so that you don't have items shifting out the bottom of the list, which would be kind of weird. And so we also animate that growth so that it is completely in sync with the shifting down of the item. So it just looks like the whole list is just sort of growing and everything's shifting down all at once to make room for that dragging item. Now there is a lot of nuance and sweating the details in this placeholder animation thing. If you are interested to go even deeper into that problem and find out a bit more, I've written a blog called Beautiful Interactions, which is painstakingly long, but it does go into some of all the little micro interactions around that placeholder. Cool, so we're dragging an item and things have moved out of the way and we now want to drop that item. What are we going to do? So our collision engine kicks in again and we'll figure out where this item is going to end up and how far where it's got to go to get to there. And again, we're going to use a CSS transition to move that item into the list. Again, we're using CSS transition to offload as much work as we can to the GPU. Now, this CSS transition is special. We dynamically generate the duration of the transition based on how far the item has to travel. So the further the item has to travel, we ever so slightly increase the animation duration. And that's to try and sell this illusion of physicality. Like when you're moving physical objects around, they have weight and it takes things longer to get further distances, right? So that's what we've tried to incorporate here. We've avoided using a spring to do this. We actually kind of get pretty much the same visual experience, but we can offload that work. Instead of doing it in the CPU, we can offload that to the GPU. Cool, so you get that nice little drop animation there. All right, now just while we're talking about the drop animations, just so you know, I've slowed them down here, but they are interruptible, so that if a user starts another drag while that animation is occurring, we'll quickly flush that animation so that you can keep working. The idea is we want to maximize interactivity. You don't want to be sitting there as a user like waiting for an animation to finish before you can do the next thing, right? You just want to be able to do stuff really quick. People probably won't run into this because the animations are pretty quick anyway, but it's just good to know that this happens. Okay, up till now we've talked about how to do drag and drop with a mouse, but the same would be true if you were using like a mobile. But what would you do if you couldn't actually see the interface at all, right? And this is a lot of people's reality. Like, how do you engage in a drag and drop interaction, which is inherently quite visible, without even being able to see the screen? So you're probably going to want to use a keyboard because your mouse isn't going to be much help to you because you're not going to be able to see where it is anyway. So you're going to be using a keyboard to get around, and you're going to be relying on audio cues to understand what's going on. And people use screen readers to give those audio cues. So how does RBD get this to work? So firstly, we add a tab index to that dragging item so that you can get to it, with browser focus. Step one, cool. All right, now we're going to add some ARIA attributes. So we add role and role description to that element. So as a screen reader, we can tell a screen reader this is a draggable item. Cool. We also create a hidden element on the page that contains usage instructions for drag and drop. So elements have a lot of accessible properties. One of them is a description, and a use case for that is giving usage instructions. So what we do is we create this element, and it has an ID, and we put all the draggable items, we point to that hidden element with that ID. Now, RBD will ship with this text out of the box. So you as a consumer of RBD don't actually have to worry about this at all. Like, it'll just work, which is pretty amazing with English. All this text is overridable like through props. So you can just kind of override it to either be more internationalized, or you can change the language if you want to. But RBD will manage that hidden element for you, so you don't have to worry about anything like that. All right, so the user's focused on it. They've pressed spacebar. Our keyboard sensor has kicked in and said, you wanted to start a drag. We then use a live region to tell the user that the drag has started. Now, a live region is a bit of an accessibility escape hatch. You can use them to force the screen reader to read out arbitrary text. So we create a hidden element and we put text in there at various times that we want the screen reader to announce to people. So they've started the lift and we tell them, hey, that lift has started. Okay. The user has now pressed the arrow key to move it into another spot. And again, that live region has told them that shift that has happened. Now, this shift was caused by our friend, the collision engine, which is back again. except this time it's working in a very different mode. Before we saw it working as a small physics simulator. Now it's just sort of working in a more instruction-based mode where you're saying, hey, move up, move down, move left, move right, and it's going to force things to be displaced to match that instruction. Right? It's not caring about items' weight or their edges, it's just getting it into the right spot. So the collision engine helps us to do that. Cool. Then again, the user presses the arrow down key, the keyboard sensor translates that, and we tell the user that they've moved it, all great, and then they press spacebar again and they've dropped it. And again, we put more text in the live region to say, this is what you were dragging, this is where it moved from, this is where it moved to. Cool. And again, all that text is customizable by people using RBD. All those different steps. Now, in a talk about smoke and mirrors, like this isn't smoke and mirrors. So let's actually take a look at what this looks like.
Mo quote, sometimes life is scary and dark. Draggable item. Press spacebar to start to drag. When dragging, you can use the arrow keys to move the item around and escape to cancel. Ensure your screen reader is in focus mode or forms mode. You have lifted an item in position 1. You have moved the item from position 1 in list BMO to list fin in position 1. You have moved the item from position 1 in list BMO to list fin in position 2. You have dropped the item. You have moved the item from position 1 in list BMO to list fin in position 2.
Yeah, thanks. Yeah. And that ships out of the box with RBD. So even though you're maybe just trying to get something that looks and feels great, like you're actually getting experience that works for everyone as well, which is amazing. Sometimes magic is just spending more time on something than anyone else might reasonably expect. That's a quote from Penn and Teller, who are famous magicians. And that's been my experience working on RBD. The illusion that RBD provides is the result of a lot of failures, exploration, and experimentation. And my hope is that as you engage in creating your own illusions, that you would be able to use some of the tricks that I mentioned today, or they would inspire you to try something unusual. Just a note of thanks before I finish up. Thank you so much to everyone at Atlassian and in the wider community as well who has contributed to this library. It's definitely not a lone effort, and I just want to thank so many people for their encouragement, for their contributions in getting RBD to where it is today. Feel free to come up and say hello to me if you have any questions. I'd love to hear about some of the stuff and crazy illusions that you guys are working on as well. All right, thanks everyone.